Welcome to the next video in the measure and integration video series. And in the previous video, we just ended by successfully finding the formula for the nth coefficient in a Fourier series. Now, it is somewhat remarkable. I know we skipped a lot of details, but in just 10 minutes, I was able to give what I hope was a decent explanation of the deep and powerful subject of Fourier analysis. Of course, it's a whole semester long course. I don't mean to minimize it, but it is incredible that it is so straightforward from basics. But in a sense, it's not that basic because it is flawed, right? There is a mistake in the steps that we went through in the exercises above. And it's a challenge, right? Fourier himself did not think there was any issue with anything that we have done, right? When it was brought to his attention that one particular step was possibly problematic, he kind of brushed it aside, if I'm remembering the history correct, and said, "But no, I'm sure it's fine," right? So like the issue is a very subtle issue. See if you can spot it for yourself. So I'll give you a second to pause and look for the flaw. But when you return, here's how it goes. Okay, so we're looking at the integral of this thing, right? So we're going to pick it up here. And if you think about, going from here to the next step, where all we do is we distribute the cosine into the sums, and then we start distributing the integral also into the sums. And actually, so far as stated, up to that point, there is nothing wrong. Every one of those steps just uses relatively well-behaved distributions. But the issue comes with this middle term where instead of having the integral on the outside, it now switches with the summation and moves to the inside. That is the problem spot, which is not fully guaranteed to always be correct. So what we would like to understand, and by the way, we're going to go ahead at this point and abstract away the cosine functions, right? Because what we're really interested in is whether or not the integral and the sum exchange, and although we're particularly interested in it because we are interested in this step of Fourier series development, this question of whether the integral and the sum exchange probably shouldn't have very much to do with only the trigonometric functions, so we probably ought to just think about general functions and what properties of functions would allow this interchange to happen. And in particular, if we're thinking about like reasons why we might think that it ought to happen, why it ought to be valid, well, if you replace the upper bound with a finite number, right? If you were not talking about an infinite series, but instead just a finite series, we know that that interchange is valid because that is effectively just the use of the sort of like distribution of integrals over addition, right? Like the so-called linear property of integration, which, we usually state for two functions, but if you just generalize it, there's just a very simple proof by induction that this works for any finite number of sums. But of course, just because it works for the finite case does not satisfy us that it will work for the infinite case. And in fact, it turns out not to always work. Now, let's try to prove it though. Like, let's just go through some steps to try to prove that it does always work and see where the proof breaks down. If we took the limit in the finite case, if we took the limit with m going to infinity on both sides, on the right-hand side, it works out perfectly correct, right? Because that m is just on the outside and the limit just turns the finite series into an infinite series. But on the left-hand side, the limit is on the outside of the integral. And if we could just pass the limit over the integral, then everything would work out just fine. But now that becomes our new question, right? Like, we actually don't know whether we are justified in passing a limit over an integral. And so, again, right, so although we were interested in sums of functions, again, that doesn't seem like it really, like the sum seems not to be the interesting, important feature here. And instead, we're actually more interested in just whether limits generally can pass over an integral of any sequence of functions, whether they came from a sum or not. So yet again, we kind of generalize, right? We drop the specific structure that we were working with and talk about just any sequence of functions G sub m, whether they're a series or not. And so now we're just interested in whether or not the limit passes over the integral. And it turns out it does not. So in the next exercise below, right, exercise number 4, you're going to see a specific example where if you tried to perform the interchange, you would get the wrong answer. So you can see in this exercise the specific function 1 over 1 plus mx. And if you took the limit as m goes to infinity on the inside of the integral, as you see in part 1 here, the result is going to be 0 when you integrate. And if you took the limit on the outside of the integral as m goes to infinity, then you get infinity. Now, you can quibble with this. You can say, but it's not an integral from a to b where a and b are finite numbers. And, okay, well, there are other examples, but they get kind of hard and tricky. So I wanted to just focus on this relatively simple example. But the point is that we can come up with examples where swapping the limited integral does not work. And the goal now becomes to try to figure out when we are and are not justified in swapping limit and integral. That really is the fundamental question that gets this whole subject going. And for a while, historically, a bunch of mathematicians worked on how you could do this. You may even remember from an earlier real analysis course that if the sequence GM converges uniformly and everything is integrable, right? So each GM is integrable and they converge uniformly to an integrable function, then the swap of limited integral is guaranteed. And historically, that was a big breakthrough, right? When mathematicians finally found that out, it did a lot of the work that they needed it to do. But what they found was that it was a sufficient but not necessary condition. So what that means is that although uniform convergence guaranteed the validity of the swap, there were other functions besides the ones that converged uniformly that also could guarantee the swap. And so like you kind of want a necessary condition because that would tell you that, like you've captured all of the possible cases where the limited integral swap. So this became a real cottage industry of mathematics, is to sort of push this theory further and to find further conditions besides just uniform convergence that a sequence of functions could possibly satisfy and still justify the interchange of limit and integral. But it got really hard. The proofs, they would make such specific constraints on the sequence of functions. And so you're getting very rare and unusual sequences of functions. And the proofs are so long and hard that like nobody can follow them anymore. And it just, the reward per unit of effort was so burdensome that this was starting to become a failed project historically. And this is the environment that Lebesgue entered into. And he had an idea that maybe the problem is actually that the choice of how we're doing this integration is not ideal for the purposes of exchanging limit and integral. And so he thought maybe if we invented a new method of integration, it would give us easier proofs for the situations when limited integral exchange. And so that was the real motivation for this new theory of Lebesgue integration. And so in the next video, we're going to see how that goes. What is Lebesgue integration?